Welcome everybody to this new session of the Chilean probability area. Yeah, we happen to have this time a friend of the channel and of all of us, Joaquín Fontbona, who will discuss about a stochastic collision and picture of the wave kinetic equation. Okay, so thank you very much to the organizer for the opportunity to this talk. And I'm glad to be able to tell you a little bit about the joint work in progress with a couple of colleagues, Roberto, whom you know very well, Armand Bernoud from University of Lyon, and also Giorgio Kristulovic, who is a physicist, Chilean physicist lives in France. And so the title is Stochastic Collision Picture of the Wave Kinetic Equation. So I will first of all give you an idea of what the main object in the talk is, the Wave Kinetic Equation, why it is important, why this has become a bit trending these last years, although it's an object which is exists for quite a long time already. Well, then I will give some ideas about the spatially homogeneous Boltzmann equation, which is an object on which I have worked much more, especially with Roberto, and I will give some basic ideas on the way one way of looking at this object, the Boltzmann equation, from a probabilistic perspective. In particular, there will be an object called the nonlinear process associated to this equation. There will be particle systems, which are known as Kack's particle system. I will say a little bit about how they came to existence, these objects, and also on the notion of propagation of chaos, which is also an old idea from Kack, which has been studied a lot in the last decades in associated to particle systems of kinetic type and kinetic evolution equations. Okay, and then I will come back to the wave kinetic equation. So the idea here will be to make a parallel. I mean, it's a parallel which is already known from its beginning between these two objects, but we will give an interpretation of this wave kinetic equation from a probabilistic viewpoint, relying on what we know from the Boltzmann equation. So that's why it's new. And so we will draw some parallel in the two objects and introduce analogous objects, as in the case of the Boltzmann equation. And that's the point where some interesting questions arise, and the questions that we are studying at this time with Roberto and Armand, and also with Giorgio from another perspective. And I will say a little bit about these results and what is the plan, the research plan for the years regarding this problem. Okay. So what is the wave kinetic equation? Okay, I don't know if anybody has heard about it. You know, Giorgio. So maybe just like a personal experience with this. I wasn't aware at all of this object like 3 years ago, well, more, around 4 years ago, yeah. And then, Giorgio came here to Chile. He comes every year, and he made a talk in the PDE seminar. I mean, he contacted Claudio, and actually, well, I will show you the equation, but it's something that is very, from the probabilistic perspective, something that looks like that you could do something with it. It has a probabilistic sense, but Daniel is not convinced.
No, it was a probability.
It was a probability seminar.
We invited Claudio.
Okay. Very important corrections. So, okay. So, this started. I started thinking about this like 3 years ago, and at some point last year with Roberto, we said, okay, we need to really think about this subject and see if we can say something from our point of view. So this is the origin. That was the origin of this work. But okay,
going back to the equation, this is a cubic integral partial differential equation. It looks very complicated, you will see. And it describes the evolution of the energy spectrum in a weakly interacting nonlinear wave system. So I am not an expert in weakly interacting nonlinear wave systems. You can ask Claudio. Claudio, for instance, is much closer to this type of models. I will give a little bit of context about that in a while, but let me say that it's what is called a effective model in wave turbulence. And what is wave turbulence? Wave turbulence is a topic in physics which has a lot of explains a lot of phenomena in contexts like plasma physics, oceanography, nonlinear optics, etc. Okay, so it's a very, I would say, transversal object in physics, and also wave turbulence. It's also related to the theory of the turbulence in fluids. Maybe you don't know, or maybe you do, but the theory of turbulence is a more or less phenomenological theory. There is not a precise mathematical framework, a fully rigorous mathematical framework established, but it's a theory from Kolmogorov. It's one of the, I would say, important, very big contribution of Kolmogorov to science, besides all the probability theory and what we know in mathematics. And it's really people who work in turbulence. It's like God. It's like Kolmogorov said this. This is the law of the energy spectrum of Kolmogorov, and it's really a very useful tool. It's not only a theoretical tool from the physics point of view, but it's really something that is used for a lot of phenomena, for understanding a lot of phenomena around fluids. Okay, so yeah, so this equation, as we were saying, was first derived by Peirons. Peirons, okay, in the 20s, in the context of quantum mechanics. And interestingly, and this is also a reason why I became interested in this type of equation, it appeared again in the 60s in works by Hasselmann. Maybe you have heard of Hasselmann, but Hasselmann was Nobel Prize of Physics in 4 years ago or something like that. It was at the same time as Parisi. So he was the one with the Japanese guy who received that for the modeling of climate. Okay. And it turns out that you can look at the papers of Hasselmann, and the papers, I don't know if they call exactly like this, but the models are stochastic. They're stochastic models of climate. And all the contribution of Hasselmann is, which was later used to construct climate change models and to understand why there is an effective, a real anthropic effect, is that he understood how the transfer of energy occurs at different scales in the atmosphere and also in the ocean, and also in the interaction of the two. So we have different scales of time, of size, okay, and it's also related to what I said about the Kolmogorov's turbulence. So there are many cascade effects, and the question is, how is the energy transferred from large scales, for instance, because you have tectonic movements, or you have large waves, but you also you have wind. So wind affects us at some much smaller scales in the surface, and also this is circulating. There are cascades in the two ways. So it's very this wasn't very well understood until 50 years ago or something. Okay, and the name of the equation is sorry.
No, eso quiere decir que no me interesa la semana.
Yeah. Okay, so it relates analogous to the Boltzmann equation in kinetic gas theory. So in the sense that it predicts the energy transfer across scales, which are reversible, and in the setting of turbulence or fluids, it's in general waves. It's related to what I said, phenomena like energy cascades or polarization. Yeah, and to keep in mind, this is an analogy. It's not that easy to understand, but you can imagine it. There is a parallel between particles in kinetic theory. which are actual particles of let's say atoms, molecules, and in wave turbulence, particles correspond to what one could call linear waves, or also called phonons. Maybe you have heard the term phonons. It's like a mechanic quantum of energy. Okay, it's a particle of sound. It's an individual wave. So phonons is phonons. Okay, just to see the type of object related to which are the basic objects in this theory. You can look at the Schrödinger equation. The Schrödinger equation has what are called plane waves, the solutions which are this form. So this is typically a form of a way of writing a wave. And if you look for solutions of this type, you will see that you have this relation between this parameter omega, which is the frequency, and k square. The k itself is called a wave number, but so the square corresponds to nf. K corresponds to momentum. Think of it. And in terms of these solutions, you can construct more general solutions. This is a linear problem, so you can obtain a general solution as superpositions. These individual, let's say, solutions, and well, you need some conditions here. This must be some L2 functions in order that these solutions are physical. Okay, so just to show the Schrödinger equation once, I am not going to talk about the Schrödinger equation. I'm going to mention it one more time, but then it will be only this object and Boltzmann equation. So this is what is called the Wave Kinetic Equation. Okay, so it's an equation, let's say in RD, that can be 2 or 3, and it's an integral partial differential equation. In terms of the only derivative is here is in time, and this looks quite complicated. Here there are delta masses, so this is really like a shorthand notation for several things. So the solution here is n. So I'm writing n1, n2, n3 for the same solution, but evaluated at different variables. So we have the variables k1, k2, k3. The variable k is, these are integrated, and the variable k is the variable of the solution. Okay, so that's why it's an integral partial differential equation. Here it's integrated in the right hand side. Okay, and as I said, these are Dirac masses, so it means that there is a relation between these variables. So these are Dirac masses either in RD, so, and this sum of things must be 0, and also in R, so these two must be 0. Okay, so that says that actually that is modeling the fact that this is modeling interaction between waves of different wave numbers. Okay, in average, and what this is telling you, the deltas, is that the waves that interact, there are 4 waves, and they belong to what is called the resonant manifold, which is just the quadruples that satisfies this relation. Okay? So you can think of this as a conservation of momentum in each interaction, and this is a conservation of energy.
Okay? Just understand, it's like you are just integrating over the natural measure of that manifold. That's why the Diracs appear, but it's just like a one. It's like just a d-dimensional thing, not an RD3.
There is a. Let me see the dimensions, but there is. I will write it in the weak form, which is much clearer. But yes, I mean there is a Dirac mass in a manifold. But I would say some of the problems we have to understand this equation is this way of writing it. I mean, it's really, you will see, it's much simpler than what it looks like written like this. The nice thing here is that it's very symmetric in the 3 variables. And if you take a test function and you integrate, well, it's still more symmetric when everything is integrated. But the thing is that, so this is more or less telling you, as is written there, N is telling you what is the spectrum density, or let's say mass of particles or waves which have a given wave number k, is a wave vector, okay, and a time t. Okay, so there's no spatial space here. It's really the domain here is RD that represents momentum of wave numbers, momentum vector. Okay. So, well, this equation has interesting conservation properties. It preserves mass, it preserves the identity, okay, and it preserves the norm of k, the norm of k, which corresponds to a mass, momentum, and energy. Okay?
So just to get it, n of k is negative, can also be negative. No, it's not a positive thing.
It's positive. It preserves also positivity.
And it is integral then.
There are interesting non-integral examples, but it's integral. It's supposed to be. It's supposed to be mass, to be probability.
Yeah, so that's supposed to be probability. It's like a probability in which the first and the second moment.
Yes. Yes. So when I say mass, it means that I can normalize to 1, so I can work with the probability. Yeah, so there are some interesting phenomena which people try to represent it with this equation, and it's possible. The first of them is what's called Bose-Einstein condensation, which is a phenomenon which appears a lot in quantum physics and superfluids and other related topics. And the idea is that you expect in some situations to observe concentration of mass at zero energy. So the equation at some point starts developing a direct mass at zero, okay? And well, there is some balance because cannot go completely to zero because you have conserved energy, so the solution must be spread at the same time in some way. And also there is what is called these Kolmogorov-Sakharov solutions, which are interesting, very interesting from the physical point of view and the point of view of turbulence, because these are same scale invariant solutions, they're similar. Power law type. So they are supposed to describe precisely this idea of a cascade phenomena where you look at some range of the, let's say, the energy, and that means a ball in this space, or annulus, and then you expect to observe the energy to go from one extreme to the other, and the mass actually the other direction. Okay, but these solutions are don't have finite mass. But there are and the behavior that is observed is more or less what is predicted by the turbulence theory of Kolmogorov. That's why it has the two. Yeah, and regarding mathematics of this equation, there are a couple of, there are several results, but the study is rather recent. Let's say it started like less than 20 years ago. So there are well-posted results, rather recent. In general, they are local in time, and one can show actually that there are blow-ups for this equation. So it's not, you don't necessarily have a solution always defined for the whole positive interval. People is also interested in the isotropic case, and it has been studied quite a lot. And very recently, a couple of years ago, 3 years ago, there is a very there were a series of papers by Hani and Deng. These are people in the US. There is an but there is they succeeded to do is to obtain this equation, deduce this equation from the what is called the cubic nonlinear Schrödinger equation, okay, which describes waves that are interacting, but at some quantum level. But it's very. This is a very hard paper actually. It has 100 and more pages. Took like 2 years for people to really like read it and have understood that it was correct, and don't have much intuition about this. But let me just mention so that to so that you see the connection. So this is the nonlinear Schrödinger equation. So this is more or less, I mean, well-known object. Even I mean, here, some people work at this, are working this equation. This is in the torus, but actually, so what you do, so here it's no linear anymore. You have this nonlinearity, which accounts for some type of interaction between the between waves, the waves that can be represented in the sense that I was showing before. And if you assume that the initial condition is random in a way, so here its Fourier transform is given by some smooth function of the wave number times some ID random variables. Then there is a scaling limit in which, okay, this is in a cube. You take the size of the cube to infinity, and you take at the same time to 0 this alpha, which is the parameter that measures the interaction. Okay, so there is a scaling limit in which this object, okay, which is it's not clear that this is a probability, but it is if you think of as what the Schrödinger equation is giving in terms of. Okay. So this is converging to, in a suitable way, to the solution of the wave kinetic equation. Okay. So maybe this will become more more or less a famous result now, because Deng and Hani also proved this type of result for another object, which is the inhomogeneous Boltzmann equation, okay, which is kind of an open problem since beginning of the 20th century. Okay, so I will speak a little bit about the homogeneous Boltzmann equation, which is a simplified version. I will say a little bit about the inhomogeneous one, but so this is I would say the more probabilistic object in which we are inspired in order to understand the wave kinetic equation, and in particular, one of the motivations is to understand ways in which you can simulate this equation on the basis of its probabilistic interpretation. So we'll come to that a bit later. Okay, so this is the spatially homogeneous Boltzmann equation. So again, it's a integral differential equation. So here you have it's written in a different way, but we will see that they are related. So what this equation is describing is the evolution of velocities of infinitely many particles in a gas, let's say, which undergo pairwise collision, interaction which are with collision. Okay, so I will explain this. It's not necessary that you understand everything at this point, but again, there are several shorthands here. So the unknown is f. Here it's evaluated in some point v velocity, and here we compute an integral, which is the difference of, the integral of the difference of these products. Okay, so we have this f prime, which is the function f evaluated in some new variable v prime. There is a function f evaluated in some variable v star. There is there is this prime star, which is defined in a similar way. So here you're integrating respect to v star, and there is also this integral which lives in the sphere. It's just the uniform measure on the sphere. Okay. I will explain in a while what this term is. It's called collision kernel with a B. But the idea is the following. So this is representing what a particle, this gas, is how it's the probability of having a given velocity evolves. Okay. So this is, if you have a particle which has velocity v, what will happen is that at some point, continuously in time, it encounters particles which have the same law as it has. So it encounters, let's say, a particle v star, which has law f, too. Then they do a collision. So what is this collision? well, it's an elastic collision, and they exchange momentum and energy, and at the end, they preserve the two of them. So let me just I don't know if I. But there is just one drawing. So you have here V. So this mean velocity, but you have a particle with velocity V, which encounters a particle velocity V star randomly. The law of this particle V star is the same as the particle here, and let's say they choose an angle in the sphere. So this is a sphere, supposed to be a sphere. So with respect to some reference frame, they choose an angle. So this is, and then you just move the. So this is sigma vector, and here is your new particle V star, and the other one is over here V. So this is V prime, and this is V star prime. Okay, so they stay in the sphere, centered in the center of okay. And they move according to a random angle, which is uniformly chosen. Okay. Okay. So again, this equation preserves mass and mean momentum and energy, in the sense that if you put the same test function as before, things cancel, and the right hand side is 0. And yeah, the important thing is that this is a simplified version of the true Boltzmann equation. The true Boltzmann equation has two variables, the velocity and position, and it's telling you the evolution of the velocity, the density of velocity and position of a particle, which is in this gas. And that means that you have this additional transport term, because a particle at this velocity and at some point is moving. Okay, and well, the collision kernel, the collision operator, this one is the same. It acts only on the V variable. Okay. So, so this equation was introduced by Kay in the 50s, and the idea was to, I mean, the homogeneous one, and the idea was to have a simpler model in which one could study and justify what is called the chaos assumption in Boltzmann's original work, in which he assumed at some point that if you have many particles, at some point they start, even though they interact, particles become independent, okay, statistically independent, which is something which is more or less the fact that we have a product here. Okay. The thing is that this is related to the notion of propagation of chaos, which I will comment in a while, but the idea is that if you have, if you look at finitely many particles in this infinite soup of particles, you will interact with any of these k particles at most one time. Okay, so you will imagine that when n goes to infinity, you become independent of all the other particles. Okay, but still, it's not like, I mean, your law still is conditioned in some way by the fact that you're interacting. This is why you have this nonlinearity. Okay? It's not completely free objects, they interact, but and they interact with objects that have the same law as you. So this is why you have here also this quadratic nonlinearity. Yeah, and yeah, as I was saying, this has been extensively studied the last 5 decades, but a lot more in the last 2 decades, especially regarding long-time behavior, the stabilization of this distribution given by the equation, and what is called propagation of chaos, which I will explain about. And regarding this term, this is called collision kernel. It's not very important for what I'm going to discuss today, but I should say that it has this general form where you have a function of the a power of the difference of the velocities times some function of the angle, And there are two important cases for what we will be discussing, which have physical interpretation. One is called the Maxwell molecules, which corresponds to gamma equal 0 here, so you don't have dependence on the relative velocities. And there is another case which is called hard spheres, in which you don't have dependence on the angle, and the dependence on the relative velocities is limited. And there are other cases, which I'm not going to use. Okay, so from a probabilistic viewpoint, this is, I would say, one of the possible ways of understanding this equation, but which is very illustrative, I would say, and you can do lots of things with it. So, which is called a nonlinear process. So, what is this nonlinear process? It's an object that was studied in the 70s by Tanaka. Tanaka, you probably know him from a local time in stochastic calculus. So it's a jump process, okay, which is supposed to represent the trajectory or the evolution of a generic typical particle in this infinite system. Okay. So this particle, what is it doing? It's okay, it has a constant velocity, and at some time it encounters a particle at the place where it is, some other particle at random times, and according to some criteria, which if something is the good case, it will jump. It will do a collision with that particle. So what is the idea here? What is exactly the conditions? So, well, to write this properly mathematically, I will use a Poisson point process. Okay. So, and I must specify the intensity. So this Poisson process is giving me atoms. So the atoms have several coordinates. One is the time, and the others are points in RD, and a point in the sphere. And this is a variable which I'm using as a field, let's say. I will find that in a way. Okay, so what is the intensity measure of this process? And that's the important thing, is that, okay, some things are, completely standard. So this is time. This is the uniform measure on the sphere, and this is uniform. This is Lebesgue, okay, in the last coordinate. But the strange thing is that I'm asking this V star to be distributed with law Vt, which is exactly the law of my process at the time t. Okay, so this is not something that I construct from. Just define this and let it exist. I need to construct it in some non-trivial way, because in a way there is some fixed point equation here implicitly for the law of the process. I want this process constructed like this if I'm given its law, I can construct it because it is easy to implement or to define mathematically. But from the beginning, I don't necessarily have this law. Okay, so that's why it's called a nonlinear process. Okay. It's really that in order to define it, I need to know its law. Okay, so this is a very common situation in what are called mean field models in the probabilistic approach to mean field models in physics. So as I was saying, what are this V prime? There is V prime, V star. So V prime, the prime variables and star variables have the same law. So my process encounters at some point a particle, just an atom, which has some distribution in this coordinate. Is distributed in the same way as my particle is. So this is the V star. I sample an angle, and then I jump to position V prime, which is constructed in the same way as I said for the equation. Okay, from V star and V. Okay, so I go to V prime. I'll go to V prime if this is satisfied. So this is kind of a variable that fixes the rate that sets the right jump rate. Okay, so this is an acceptance rejection, let's say, variable. So if this happens, I will do the jump. Okay, if it doesn't happen, I don't do it. And at the end, the consequence is that the rate happens, the jump happens at this rate, which is the same which appears in the collision kernel in the equation. And one can show, and I'll just give 2 lines of, some lines, but just in order that you see that one can show that the law of this process is a solution of the Boltzmann equation. Okay. In this case, I'm writing it for hard spheres in order to not have the angular dependence. So how do you check that? Well, this is related to what we were discussing in the elective course. But you need to rely on the compensation formula for point processes, which tells you that, well, the difference between your value and the process at time 0 and time t is just the sum of the jumps. Okay, so this is the sum of the jumps. I mean, it would be this integrated with respect to the Poisson point process. Okay? And you have a minus here because you're. But what this formula is telling you is that you can replace this by the intensity measure. The minus that you have. Okay, see here you have minuses. Okay. So the minuses that you have, you don't care because these processes are right continuous. So the discontinuities are countable, so you don't see it here. And you get a martingale, which is what is called the integral with respect to the compensated Poisson point process. So this disappears, and if you take expectation, you arrive at this. So if G is the law of Bt, these integrals correspond to the expectation of phi of Bt. This one corresponds also to the fact that you have a function here of Bt. And this one corresponds to the fact that G is the law of Bt too. So you get this quadratic nonlinearity here. And this is exactly the weak form of the homogeneous Boltzmann equation. Okay. So in a way, there is kind of an equivalence between the solutions to the Boltzmann equation and this process. If you have a solution, you can construct this nonlinear process, but also you can construct sometimes the nonlinear process by a fixed point argument in the space of probability measures, and that's precisely what Tanaka did, and the reason why he introduced this type of process. And also, it's because you can relate it to particle systems in a way that I'm going to explain now. So, at the same time as Skag introduced this equation, the homogeneous Boltzmann equation, he introduced a particle system which was supposed to approximate this solution of the Boltzmann equation. And the idea was to prove that this assumption that Boltzmann made, that particles became independent as their number goes to infinity, was correct from a mathematical point of view. Okay? That could be justified in some situations. So this is the end particle system for the Boltzmann equation, the same for hard spheres. So let me just say a couple of words. So I have n particles. This is, again, I have Poisson measures. So these Poisson measures, they sample points, they sample angles, and they sample this filtering variable. And I have two here. I mean, one for the pair ij and one for the pair ji. So it's the same pair, but they have different roles, because let's say this means that particle I at some point decides to jump and he chooses particle j. Here is the opposite, let's say, and particle j decides to jump and chooses particle I. And the jumps are related because I must use the same sigma. I mean, one is sigma, the other is minus sigma, but I will do this for the two particles, so they are related. Okay, the two of them jump at the same time. Okay. So these are Poisson point processes which are sampling these atoms. I'm not sampling velocity which has the same law as the particle, because that's precisely the fact that I'm doing this normalization, and that when I encounter an atom, I choose a pair. Okay, so I'm sampling from the empirical measure. So the idea is that, or if you want, I choose a particle and then I choose another one different one. So the idea is that I'm sampling from the empirical measure of the system, okay, which in the limit will correspond to the law of the process. Okay, so again, V prime, V prime is the point to which towards which I jump, and again, well, my input variables, let's say V and V star, are the particles, and well, something interesting about this system is that energy and momentum are preserved exactly, in the sense that the sum of the particles are preserved by the same resonance there, and the sum of the squares are preserved. And this is actually very easy to simulate. I mean, you have these Poisson point processes, but it's actually very easy to implement because you just need to simulate some exponential variables, okay? Of what rate, you must tune it dynamically, but roughly because this parameter, I mean, the rate is not fixed, but you choose some, let's say, very large m, which is bigger than these relative distances, and then you weight exponential times of parameter 2nm, okay? And then you choose a pair, different particles uniformly, and then you decide, okay, these particles want to jump. Let's draw a uniform random variable here in the interval 0m, which is like the truncation of the Lebesgue measure atom, the atom corresponding to R plus for filtering. And if this happens, I jump. Okay. And of course, this evolves. So at some point, if this is getting bigger, you will have to consider a uniform variable in 0m for m bigger. Okay. So it will jump faster, and it will do the same process. Okay, and what is propagation of chaos? So this is the general form of a propagation of chaos results that you will find in many mean field models. The idea is the following: assume that you have RID particles from some given distribution. In this case, let's say it's F0. It's a distribution at time 0. The value of time 0 of the solution of the Boltzmann equation. Then, under certain conditions, which are related to momentum or properties of the collision kernel, you can show the following: that for each t, if you look at k particles, notice that they are exchangeable, so could be any of them. They will, their law will converge to the product of k copies of the solution of the Boltzmann equation, or k copies of the nonlinear process. So the independence that you impose at time 0 propagate for later times as n goes to infinity. For finite n, it's not independent because they start interacting quite soon, so independence is lost very, very quickly. But as n goes to infinity, and that was the idea of CAC, they will become independent for all times. And one can also show that this is equivalent to proving that the empirical measure, okay, it's a random variable, some space, also converges to this deterministic object, so which is the solution of the Boltzmann equation. So it's a kind of law of large numbers at the level of empirical measure. Okay, so this has been studied a lot since the 60s, 50s, mainly for the homogeneous case. So there are names like McKean, Kac, Snigman, Maillard. Well, more people in the last 20 years, including myself and Roberto. And you can get this type of results in several ways. For instance, you can, one of the main goals or more interesting goals is to have a result which is uniform in time, which is kind of the original idea of CAC, that was to prove that you have this propagation of time, propagation of chaos property uniformly in time. And if you can show that the convergence to equilibrium is uniform in n, in the number of particles, the rate of convergence to equilibrium is uniform in n, then you can show that also the equation converges at infinity to infinity, well, at the same rate. Okay, so the idea was to justify several things. One thing is this idea of chaos, of independence of the particles when the number is big, and also that you have convergence to equilibrium, which is the H theorem of. Well, so since we're not really proven like that at the end, but well, there were lots of things done for the homogeneous case, and for the true inhomogeneous equation, there has been not many works and not many attempts actually. So there are results by Lanford, Bodino, Raymond Gallagher, and the final result is a paper by Deng and Hani of a couple of years ago, which is also, I mean, would be an important paper. It's kind of Hilbert's problem. Yes, but they did before the before this, they did the kinetic wave equation, more or less understood how to do it. So for some time, there were results in short time, propagation of chaos in short time, and you could justify. I mean, the results are in fixed time intervals, but they couldn't justify for arbitrarily long times that you have the convergence of these particles through the Boltzmann equation. Okay. In the homogeneous case, you don't have the randomness of the particle of the Poisson process. It's just the initial randomness. So it's a matter of proving that you have Newtonian reversible dynamics converging to something which is irreversible. That's the difficulty. And okay, so. But let's just keep in mind what propagation of chaos is in the context of the Boltzmann equation. And let me show how can you use this, how you can use this to prove, to construct a particle system, a numerical method to simulate the equation. So this is a CAC system for Maxwell molecules where you don't have the dependence here on the relative velocity. I also removed the dependence on the angle, so it's very simple, a toy example. So here we have not many particles, 5,000. We could do much more, but just for the example, there are not many. And yeah, what we are showing here is this dynamics, what we're about to show, and so we have an empirical measure. The dynamics is what I said, as simulated, as I said, with the exponentials. Okay, and then you regularize the empirical measure in order to have a function. So what you get is something like this. Yeah. So keep in mind the scale, because I will compare this to the kinetic wave equation later. So this is some initial condition, and it more or less quickly stabilizes and well, supposed to approach a Gaussian distribution. Actually, it does, but it's since I don't have many particles and the grid is not too good. But I don't know, what is the grid showing? What's the height? The height here, I don't know the actual units, but
what is the speed? Is it the speed or
it's v. It's just it's not positions, it's the velocity. Okay, so
and the xy is the position?
No, this is position in space, and this is the empirical density of particles. You have 5,000 particles, so they are somewhere in space, and this is the height of
where
the
they are.
Where they are. Okay. So let's go back to the. So this is how you can simulate a solution of this type of equations just by simulating the particles. Okay, and you can give a theoretical guarantees that it's actually approaching the solution. Let me mistake here. It's rather. Okay. Yeah. So what is our contribution here? What is our interpretation of this of the wave kinetic equation from this point of view? So let us recall a little bit of notation. So I will be using this all the time. So I have the pre-collisional configurations, or which I call Z and Z star, or any name and star. And then I have the post-collisional ones, which are the primes, okay, which are constructed from the pre-collisional ones like that follows. Okay, so it's not working. There it is. Yeah, it seems that it will be. No, it's okay. Okay, so you already saw what was the weak form of the equation, of the Boltzmann equation. So you can do it in the nonlinear process, but also at the level of the equation. You just integrate with test function phi, and when you rearrange terms in a way, in a pseudo way. So the right-hand side of the Boltzmann equation looks like this. So you have this nonlinearity here, and here you have the collision rate. for which can be 0 or 1 for Maxwell and Hartsfield, for instance. And the question is, what is the analog for the wave kinetic equation? And actually, in spite of the rather complicated expression that it has, when you do the same thing, you integrate the right-hand side with respect to a test function. You need to do some computations, in particular expressing what these delta masses mean. There are so many changes of variable, things like that. But it turns out that you end up with an equation like this, where actually instead of 3 iteration variables, you have 2, because there was this direct math. You get an integral over a sphere. And if you didn't have this term, it would be exactly the Boltzmann equation, the homogeneous Boltzmann equation, for gamma, for specific values of gamma here. Okay. In the case of the wave kinetic equation, gamma will depend on the dimension. It turns out to be d-2, and you get this additional two additional terms. Okay, so that's why it's cubic. Boltzmann was quite added on this. So the question is, what is the interpretation of this? That was something that we more or less found at the same time that we understood what the weak form was of the equation was. Okay. So if you're familiar with the jump processes, in the same way as here, we obtain this by some type of compensation formula, this type of expression. Well, here you will get, here is more or less the same, but what is interesting here is that this depends on the post-collisional variables too, not also on the pre-collisional variables. Okay. But it turns out that you have also this compensation formula, you can do Ito calculus, etc., for functionals for processes which depend on the past in a predictable way, let's say less continuous processes, so the T minus, and also that depend on the atoms. Okay. So this is the case here. This depends on the atom. This is part of an atom, and this is also constructed in terms of the atom. So it's exactly something that you can expect to deal with in the case of in this case too. I mean, if you have the right objects. So what is the idea? The idea of this, the idea was to identify what the corresponding nonlinear process is, constructed. So this is exactly the same as is in Boltzmann, but we have this additional product, and the interpretation we give is the following. It's just a modification of the rate. The thing is that it's a modification of the rate which is nonlinear in the sense that it depends on the law of the process itself too. Okay. So the idea is the following: assume that we have a process. We can construct the following process. We give us this Poisson point measure. The intensity is as before, where here I have this nonlinearity in the sense that here I ask to have this atom that it has the same law as the process. And I give myself another variable for filtering. So this filtering variable, what it is doing is that it will allow or not a collision, a proposed collision, if this filtering variable is smaller than this sum. Okay? So assume this has a density. Okay. And everything is defined in a similar way. I mean, the K star, K prime, etc. So the idea is the same. So what the wave sees is is another wave at some point, random time, which has the same distribution as it does. You encounter this other wave, and you sample an angle, and then you propose two. Again, you need two results, which are the star variables. I also forgot here. I need K prime and K prime star, which are constructed like that from my KT minus and my K star. Okay, and I need the two of them. And I evaluate this this filtering variable, and I evaluate, the density of the solution. I mean, the law of the process at these 2 points, which are the post-collisional points, let's say, and I filter the collision according to this. Okay. So Yeah, so this is tuning the jump rate, these two variables, theta and chi, in such a way that you get this as the jump rate. And one can show that if you have a solution to this process, to this equation, the law of the solution is a solution of the kinetic wave energy. Okay. Okay. So, and you can associate a jump particle system to this process, and the idea is to use it to approximate the process. So it's similar as before, with one important difference, which is that I would like to filter according to, the post-collision, according to the post-collisional configurations, according to the value of the density at each point. So this is what is here. Okay. But the thing is that for finite particles, I don't have a density. I have an empirical measure, an empirical density. So what I need to do is to regularize the empirical measure, which is what I'm doing here. Okay. So I have a particle system which needs this regularization parameter, depends on epsilon, and this is the empirical measure, okay, of the system. And the dynamics is the same. I need two variables to filter, but it's easy to implement, and one can do it. One interesting thing is that it preserves exactly collisions at each energy and momentum at each collision. To speed up a little bit, and we expect, and we have partial results in that direction, that you can prove propagation of chaos for fixed epsilon. Okay, so first for fixed epsilon, in which case this should be the limit. It's not. The nonlinear process we originally proposed was like this, but since we have this convolution with a modifier for the empirical law, we need to add this and the nonlinear process. And the equation that we should obtain is the following. So it's more or less the Wave Kinetic Equation, but these two terms, they are convoluted by this modifier. Okay. Okay. So what is interesting is that this is a kind of random regularization of what is called the resonant manifold, so the constraining energy and momentum. And this is something that, from the PV point of view, people try to enlarge the manifold, to enlarge the delta mass, but yeah, so they don't have exact preservation of momentum and energy. In our case, we have at each collision, but then we sample and we filter to decide if we keep the collisions or not. Okay, so let me show you simulation of this. So the particle system it's also easy to implement for fixed epsilon, and this is what you observe. So the original condition is the initial condition is the same as for Boltzmann, and the scale is the same. And what you observe is the behavior which is similar at the beginning, but then it makes this, which is so clear if it was expected for us, but in several cases it is expected. But this was like a very simple case. It already gave us this, which is something like a condensate. So you really get like a concentration of the particles at the origin. Okay. So let me just say a couple of words of what we're doing now. Yeah, so what have we done so far? There is something which is quite easy. That is that if you have a solution of the equation, you can construct the nonlinear process. The nonlinearity of the fixed point is already solved in a way by the law, and then you can use that law to construct a nonlinear process. So that is easy to do. The thing is that we are also interested in doing that for the regularized process, and then show that when epsilon goes to 0, you have the convergence to the true process. Because what you want to do at the end is do like a diagonal limit. You take n go to infinity and epsilon going to 0 with n in a suitable way. Okay. So to do that, you need to do everything uniformly in epsilon for the nonlinear process. And the thing is that you actually don't know if you have global solutions, so you have to work in a short interval where you're able to also show that you have simultaneously for all epsilon positive or 0 a solution for the equation. Okay, so that's something we have already done. We have a global well-posted result for the modified model. Actually, the modified model is much nicer. You can deal with it with other techniques, not analytical, more probabilistic. So you can prove a global existence and of this nonlinear process, propagation of chaos, and so on. The thing is that we don't have a quantitative result yet. You need a quantitative result because you want to tune the epsilon in terms of n in order to have the diagonal convergence. So this is something we need to do still. And just some perspective of what we were planning to do in the future. So first of all, yeah, there is this convergence that we want to prove for the equation as regularized equation to the true equation as epsilon goes to 0 in a quantitative way. This is what I was saying, that would provide us a propagation of chaos result for this regularized system towards a solution of the Wave Kinetic Equation. So the interest here is that we will obtain the equation as a limit of a particle system of the type of CAC, which are stochastic and which are you can easily simulate, and not from the nonlinear Schrödinger equation, for instance, which is quite complicated. It's really complicated to implement and to show also. Secondly, thirdly, yeah, can we prove something about this condensation? Because I mean, something which is conjectural in some cases it's proven, but for this, we would like to understand what happens in terms of the particle system too. And yeah, so this is a tool or a way of to formulate the problem and study for this conform. Then there is a question on what is called the Kolmogorov-Sakharov solutions, which are, as I told you, there were subsimilar solutions, which are like steady states. If you look at some range in the energy spectrum, it's supposed to be stationary, but it's supposed to describe the cascades of energy. The things that is not finite, infinite mass, but we think that we probably can have an interpretation in terms of stochastic jump process in the middle, in the good range. It's called the inertial range, and then probably we'll have an infinite mass. So that means that you have infinite Mele collisions, which is more interesting from the theoretical point of view and more difficult, but it's more interesting. And there are some other questions, rather physical. One is related to spontaneous stochasticity, which is actually what happens when you have a blow up. If you have a blow up in the limiting equation, physicists they like to study what happens after that, because when you have a regularized model, typically the model can live longer than the blow up, and you would like to see what happens when you remove the regularization. And what they show is more or less empirical. What they find is that you lose uniqueness, and right after the blow up, you have a random solution. So that's what it's called. Why it's called spontaneous stochasticity. There are some normalizations. It's a bit complicated, but it seems to be a relevant question. And also, the idea would be to implement this method in the simulation method in actual real scale physical models. Okay. So that's also something we want to do. Yeah, conclusions. That's the conclusions. More or less what I said. So thank you.
Are there any questions here in the chat or in the?
I have a question. I don't know if it's a good question. So in the Boltzmann equation, it's not. I think you said, but the other one is phenomenology. Like in the Boltzmann equation, you can see what's going on.
Mm-hmm.
Why you would, and for this wave kinetic equation, no. well, I don't know what they're trying to model, but can you say something like physical? Does this interpretation give you something that people can sort of make sense of what's?
I think maybe the first interesting thing for physicists is that it's really like giving an interpretation of what, how you can respect let's say this rational manifold, okay, this constraint for the post-collisional variables in a smooth way, in a sense, because if you really work with the deltas, it's very singular, and it's not clear for intuitively what it means. I mean, for me at least, but also for physicists, they don't see exactly what's going on with the interaction, what happens with the energy, so they need to regularize. Okay? And when you regularize, you lose the constraint. You're not preserving energy when you regularize in the physical way. Okay? So what is interesting here is that we have a way in which the interactions preserve exactly the energy and momentum, but by filtering how many randomly which collisions interactions you allow or not, it gives you it makes compatible the two things: preserve energy exactly, but also satisfy the constraint for the post-collisional. So I think that's something which is appears to be interesting for people with whom physicists with whom we have. And the other thing is the possibility of simulation, because simulations here are very expensive because they need to do integrations, they need to well, they use Fourier analysis, they use lots of stuff, but there is not a general way of simulating.
This is the sort of thing that Giorgio was using these large clusters to simulate? Right.
But okay, what I showed here is 2D. If you want to do in 3D, it takes more time. But it's just because you need to keep more things in the relative velocities in memory, and you filter a lot more. So there are lots of collisions that are not done, and so it's wrong. It's wrong. But still, it's direct. You don't need to cook up things in order to, and you don't need to integrate. What no, you don't need to compute actually. So that's a good thing.
So I got lost a little bit in the. So why all of these, both the Boltzmann and the approximation of the Wave Kinetic Equation, have this variable that either accepts or rejects? It's like, why don't you always? Because somehow my idea of collision is that you cannot reject a collision, especially when you're in a car. Please don't. So what is it?
But probably. Okay, two things. First is that it's not for the homogeneous Boltzmann equation. It's not actual collisions, because so that's a simplification by Kak. But if, the equation assumes that the distribution of particles with a given velocity is the same over space. Okay, so so in order to represent the true collisions. That's why you have this operator, the collision kernel that appears, because the two collisions occur because of physical forces. Okay, so in a way you're already cheating a little bit, in the sense that the collisions are. I mean, if particles are size 0, you don't really collide. You collide because there is you get too close in a way at some scale because of some force interacting. So. Yeah, so from this point of view, it's not a problem to suppose that collisions are random in a way.
I see. So it's not like you are following particle by particle, like menistically, you say like this particle will crash with a particle of this velocity with this probability.
Yes.
I see. So that one and somehow
but for the true inhomogeneous equation, Boltzmann equation, it's I mean, you collide. For hard spheres, when you get closer to some epsilon, it collides, and otherwise it doesn't collide. So it's really exactly.
And for this approximation of the Wave Kinetic Equation, you have this other post-collision also.
Yeah.
So like you saw the past and the future, and you decide whether you crash
Yeah,
seeing the future.
yeah.
And that's what is like.
Yeah, and that's a little bit strange. I mean, it's strange enough, but why not? I mean, it was it was I would say it was like a barrier to imagine to give an interpretation. But then we allowed us to do that. It was okay. Why not? Okay. So and it works. Fortunately.
So there should be like a true, like also physical interpretation, like with Boltzmann, that they are like colliding and.
The case of Boltzmann, I mean, the homogeneous.
Yeah, the wave kinetic equation, because you have this post thing. It doesn't look that physical. So should there be like something harder in the sense of harder to keep track of? But,
yeah, I mean, in Boltzmann, you just you decide to propose a collision and you just jump. You don't need to check something at the post-collisional configuration. But for the energy transfer in wave kinetic equation, there needs to be one wave at the wave number.
Possible one.
Yes. Interestingly, you don't need the two of them. You need just one. So you have this this interpretation. So I collide with some wave. I interact. I have some random proposal of new wave numbers for the two of them, and I need that at least one is there is mass at least for one of the two post-collisional proposals. That this is positive. One of the two. You don't need the two of them. If you need,
and the other is the density, or it's just the probability of pain. That's like
here is the density. Here's the density. So you need to have positive density at least as one of the two post-collisional. But it's good that it's the two. I mean, you need this is the sum, so you need just one, because otherwise it would not move. It would be too rigid. But the still is more rigid than the Boltzmann equation, because the Boltzmann equation you just jump. But here you need to check that there is some mass where you want to jump. For one of the two, there need to be some mass already. This is why it's much slower. And then when it starts, concentrating, it will insist in points where there is already mass. That's what you.
But intuitively, you are just losing a constant in the mixing time, or you are.
It's no, it's not just a constant, because it's nonlinear, and it makes that it's very slow at the beginning, and once you start having concentration, like the condensate, it starts being very fast there.
Are there further questions? We cannot hear you or neither see the chat. So we can ask Joaquín. He's around. He's going to be around for a while. So you can ask him. So let's thank Joaquín again.
Thank you.